Last time, we finished up by seeing how we could choose sets to represent formulae of our language, just as we choose sets to represent the natural numbers. What we're going to do with that is to see how we can then, in a set theoretical way, talk about truth in structures. So we'll look at the so-called Tarskian definition of satisfaction, and we'll see how we can express set theoretically what it means for an assignment of free variables in a formula makes the formula true in a structure. Now, we could do this in great generality, talking about any first order languages and any kinds of structure. But we're only going to be interested in the applications in this course for the language of set theory, which just has epsilon and equals in. And the structures we will all be interested in will be of the form class or set X with the epsilon relation and no others. So that's where we will be going today. But just to review or catch back where we got to before and last time, we were thinking about coding formulae by code sets. So I can take a formula and I can just think of it as a little tree, right? Here's the tree it represents. A formula is always finite. And it's built up from atomics, kind of the leaves of the tree here, by a process of adding on quantifiers, negation symbols, or taking a disjunction of two formulae, which is where the tree branches. So I can sort of analyze this formula here into this tree with these two atomics that's in it. So I can then say, well, if I've got codes for these guys, and I know how to code something to put an existential in front or a negation and so on, then I can just recursively assign codes to all the components of a formula till I end up with the code for the formula itself. And what we saw was we actually used products of primes here to code atomics. And we then used some pairing functions, unordered pair sets to code other objects that are down there. So what we're going to see, right, is that this is an absolute process, and we're going to use these codes as part of our way of defining satisfaction. So first of all, we'll write down a definition that will show us what it means for a set to be a code for a formula. So I'm looking then at definition 312 on the top of page 46. Let me just put that there in front of you here, rather than writing it out once again. Let's just see then here what it says. So actually it comes in two stages. We define this function fml, and it returns either a 1 or a 0. And it defaults to 0 in most cases, but if, on the other hand, it'll return a 1, and the idea is that f is a building function. It tells us how to build a code for the formula u in n steps. So you can see here, f of n is u. The domain of f is the natural numbers up to and including n, 0, 1, 2, 3, 4, and so on up to n. It's a function into the hereditary finite sets. And now the rest of the clause here just specifies what we saw in the previous definition, how to code things up. So for anything that's in the domain of f, there's just a number of possibilities. Either f of k is the code of an equation, vi equals vj, or it's a code of an epsilon, atomic epsilon, Vi is a member of Vj, or f of k is a code of two earlier things in a disjunction, thing coded by Fm or thing coded by Fl. Or we've got here a negation. F of k is the code of the negation of the formula coded by Fm. And here we've got the existential quantification. F of k is the code of the formula coded by Fm with an exists Vi in the front. So the F gives us how to construct the code for U, and it does it in n steps. So I'm not particularly arguing that there's a unique way of writing this down. After all, I didn't specify which order these atomics were written out. It doesn't matter. It just means that there is this function f in n steps codes U. So U, this is a set, will be a code of a formula, and the function will return a 1 if there is an n and there is a function f which will build U for us in n steps. Otherwise, the function fmla returns, it defaults to 0. So in this way, we've got set theoretical functions, the characteristic functions of code sets of formulae of our language. And what we've done here is just express things using definite terms. Here we've got bounded quantification. We know that this is definite by a previous lemma here. So it's going to be this function will be absolute for transitive ZF minus models. So such a model will know correctly whether a code set that it's got is a code set. Okay, so this is just a bit of nomenclature right here for shorthand for using for later. What we do next is look at formalizing the Tarskian satisfaction relation. So these definitions I will write out. So we'll do this. This will be this will be reminiscent of what you've done in a first order logic course. It will be, I mean, the notation is mine and it's slightly different from before. We're going to define here, this is going to be a set of valuation functions. Into the structure X. Well, it's X with the epsilon relation. Right? X is always going to be here. In this notation, X will be a set. And this is the membership relation restricted to X cross X. Okay. So let's see what it actually is. Right? So it's defined to be the collection of functions H. The domain of H is actually omega. And the range of H is contained in X. And the idea is that although its domain is omega, really only a finite initial portion of H is relevant. From some point onwards, it'll just always return the same object in X. So there's going to be some n in omega such that for all, oh, sorry, I'll stick with what I've written. So there is a y in X so that for all m greater than or equal to n, h of m returns y. So the finite interesting part of h is h0, h1, h2, all the way up to hn. From then onwards, it's just returning that last value, hn. So it's kind of a finite function, but it isn't, because we do specify the domain as all of omega. And I'll say why we're doing that in a moment. So again, piece of notation here. If I've got one of these gadgets here, and I pick something in the structure y, I'll define the valuation that is just like h, except for I, h of I will be y. It'll ignore what h of I was, but the new valuation will return y. So we'll look at h modified. So it returns y on input y. So for any j in omega, if j is different from I, then h of j is just this. Okay. But if j equals I, then it returns y. That's just a useful piece of notation to have this variant function here. So we just tweak h so that it returns y. So because I was thinking of h as being essentially a finite function with just this tail, we could write it as function h is in Qx if and only if there's a finite function into x and there is a y in x, such that what is h literally is a set of ordered pairs. It's h0 together with the collection of n y's here for n in omega, and what I've written as dom h, I just say n is greater than or equal to the domain of h0. So it makes this clear then that what we've got is a definite expression down here. You've got these bounded quantifiers here. This is a definite term. Here we're just taking the union of two things. Here I've got a little bit of this definite replacement going on to say I've got this as a definite set as well. So the idea is then that this is definite. This shows that h in Qx, this is absolutely definite. Right? So we have here then also something that's a definite relationship between h and I and y. Okay, so I'm going to think of these h's here as assigning to the free variables of a formula objects in X. So the formula can talk about the things that are assigned to its variables. So the idea is for any formula phi, and maybe with free variables v0 up to vk. So let's say the free variables of phi are contained in the set here. We can use h. We can take an h in Qx to assign objects in X to these free variables. So the idea is that vi, this is going to get assigned hi. Now, formula is a finite string, or a little finite tree, as we saw how it was built up. It's only going to have finitely many free variables, certainly no more than there were those atomics on the leaves of the tree. And so all we have to have is a function that goes from with domain k plus 1, and we're going to cover all of the free variables and assign those variables vi to hi. Point to note is that given an h like this, actually it is an infinite function. So it actually doesn't matter how many free variables phi has got. I could apply h to another function with twice as many free variables, and it won't matter because h will assign for every natural number an object in X. So now when we assign objects like this, so I've got this formula phi, and now I've substituted in, I've substituted in h of 0 for v0. And I substituted in h of k for vk. Right? So now this formula says something about these things in X. And we can ask whether, right? Does this assignment h make phi come out true? In the structure X epsilon. I mean, of course, if phi says something obviously false, if it says v0 does not equal v0, this is never going to be true in any structure. On the other hand, if it says v0 does equal v0, that's always going to be true. And then other statements will depend, right, on what happens in X. So this idea of what, this semantical idea, right, that we give this formula meaning by putting in objects from a structure for its free variables, and then interpreting it in the structure X. Right? So this is, again, this is a semantical process. It's to do with meaning rather than just talking about how the formula is formed, which is just a syntactical question. So we can ask this question and we can give a mathematical answer, or indeed a set theoretical answer, in terms of the code sets for phi and these assignment functions. And we just give this definition by recursion. And this is definition 315, which is the important definition for today. So let's go through that definition. So this is called the satisfaction relation. And this is due to Tarski. And so we define by recursion the term sat ux. And it will be a definite term. Right? So it's one could think of it as a function. Right? So we're going to do this by recursion, right, on the complexity of the codes for formulae. So we're first going to define what sat of codes of this equation in the structure X. So in here, unless this is a code for a formula, and unless this is a structure, the function will just default to 0. But in the more interesting cases, right, if this is a code for a formula, we're going to define this as to be the set of valuations that make the formula true in X. And how do I make a formula Vi equals Vj true? By assigning objects to it that are identical at the ith and jth positions. So I look at the valuations that do precisely that. Easy, right? So again, it has sets as inputs. This is a set, this code. This is a set, and this is a set of sets. These are functions, right, which happen to be from omega into X. This epsilon statement will be true as long as the function Qx, whatever it assigns to Vi, this will be a member of what's assigned to Vj. Now, if I've got a disjunction, what assignments do I need to make chi or psi true? Well, any assignment that makes chi true or an assignment that makes psi true. So I'll just say it's the union of these two. Again, nothing strange about this, right? What is it going to be to make this negated formula true? Well, if the negated formula is true, the formula itself had better be false. So it better be that we don't take assignments that make psi come out true. We want assignments that make psi come out false. So we'll take those assignments which don't make psi come out true. That I can say like that. So this is all the assignments that make not psi true. And now this existential quantifier, Vi psi, now I want a set of valuations that make this true. Well, what I could have are those valuations that assign to the free variables of psi that make this true. But what is it to make an existential statement true? It means there is something I could assign to VI to make it true. So I'll look at these valuations there, for which there is some y in x. So then now, and this is why I introduced this tweak notation, so that this is now something that makes psi true. Right, so I look at those valuations so that if I amended the valuation to return this y, this will be true. Doesn't matter what the y is, as long as this valuation makes it true, then I'll put h into qx. And the last is just the default clause. This is empty right here if this is not a formula. Right, if that's 0. Now it's more normal in logic to write, this is the first part of the definition. Here, second part. Now I'm at the top of page 47. We write x epsilon code square brackets h if h is in a collection of valuations that make x true in, make u, the formula coded by u, true in x. So we tend to use this double turnstile notation, which is sort of saying h makes u true in x. So again, it's semantics. It's about making things true or false. Okay, then there's some obvious observations. If h makes not psi true in x, so it's not the case that h makes psi true. That's what negation means, right? So we sometimes write, if it's not the case, we just strike out the double turnstile. Right, so it's not the case that h makes psi true in x. Yeah. Another point to note is, if x was actually the empty set, this always turns out to be empty. But this would be terribly uninteresting to consider. Well, it's minimal interest to consider what's true in the empty set. Right? Now, this is a definite recursion. Right? These are definite terms here. I just pick out what's in this definite term here with this property. So on atomics, SAT gives me these definite sets. And now I'm doing a recursion, which is just taking definite operations. We're taking unions, we're taking the difference of two sets, and here I'm looking at a little bit of separation. I'm looking at definite separation here. I'm looking at the H's in QX that satisfy this definite relationship here. There's some bounded quantification about these definite sets. So this is essentially the next lemma. .316 here. Sat UX is defined by definite recursion. Hence, then, this relation this is absolutely definite. So I'm not going to go through the proof of this. I'll just take this as a given. What we've got here is a recursion, which is kind of definition by cases, right? What happens in various, how we define SAT in terms of the things we previously defined, depending on the case that's down here. If one wanted to express it formally, if you insisted on expressing it formally as a term recursion scheme given a term as in the recursion part of the definition of definite, then you can do so. And that's what the proof does here. Again, as I said, I'm not going to go through here, but just see the features of the proof. I can write sat ux as being the set of h's in qx, and such as a whole long thing, right? And again, you can see here, this says that u is coded up in a particular way, and h is making these assignments. And at the end, I just say sat ux, right, is this term t that we're defining here applied to x and u, and the sat vx is for v and u. So one could spell all this out in glorious detail, right? But I don't think this is particularly worth it. So we'll skip this proof here and just assume, we'll take it, that we know that sat ux is defined by definite recursion. So there's no need to memorize that proof or pay too much attention to that there. All right, so I'll just assume that's done. So some more notation here. Here I talked about H, and I already slipped into saying making the formula U true in here. But U, of course, is a set. It's a code for a formula, right? So if U is the code for phi, okay, so we tend to write as well X epsilon phi H. Whereas more formally, I should put in the little square corners up here. Also, it's sometimes useful to display the free variables of phi and the things assigned to them. So another variant here is to do precisely that. So 1, 2 here. So if the free variables of phi are contained in Vj0 up to Vjk, whatever they are, And I've got objects y0 up to yk in X. I'm really only interested in the assignment function that sends vji to yi. I'm not really interested in the rest of such an H. So we write X epsilon formula phi, and now I'll just put in here y0 to yk in these square brackets here, right? Instead of if and only if X epsilon, where h of ji is yi for I less than or equal to k. This is the interesting bit of H, right? Here, as far as we're concerned. Now, just note this makes perfect sense because the truth or falsity of the formula just depends upon the free variables, what we put in for the free variables that are there. Perfect sense. In terms of meaning, the truth or falsity of phi on the objects depends only on what objects are substituted for its free variables. Are substituted for its free variables. What are assigned to the other variables is neither here nor there when it comes to working out whether the assignment makes phi true in X or not. In particular, if phi doesn't have any free variables at all, we call it a sentence. So it may be that, maybe it's a formula like this, vi equals vi. Okay, no free variables in there. This variable is bound by this. Then phi is called a sentence. So in logic, we would say sentence is one without free variables. And the assignment functions are irrelevant. An assignment function will make, if this is a sentence, this assignment function will make phi true if and only if every assignment function does. Because whatever it does to whatever assignments it's making to variables won't affect the truth or falsity of H. So in the case of sentences, we don't bother writing assignment functions. So phi is a sentence. We're just dealing with classical logic, right? Either phi is true or false in the structure. So in that case, we're just going to write. And don't bother writing any assignment function, or the opposite. If it's false in the structure, then we'll write this. Okay? Or not phi is true. So in this way, right, we can define truth in a structure. So to comment on this a little bit, here, as Tarski noted, to define the truth or falsity of a sentence in a structure, according to this scheme, you're going to have to define truth or falsity of formulae. So you're going to need assignment functions if you're going to define truth or falsity of sentences in this inductive way on its components. Because, of course, the components of a sentence needn't be sentences. This atomic formula is not a sentence. It's got VI and VJ free. And so, but this will be could be a component of a sentence. The reason for the main reason for taking H as a function with domain omega is that if you look in some logic textbooks, well, I think if you look in almost any logic textbook, there becomes a kind of fussy point when you try and define satisfaction for disjunctions. If you only consider functions that are long enough to assign objects to the free variables of chi, that function may not be long enough to assign objects to the free variables of psi. Psi may have 1,000,000 free variables, and psi and chi may only have v0 as a free variable. So then you have to kind of fuss about, well, this H, if it only assigned something to v0, I can't think of this as being something that is an assignment function for chi or psi, because psi has all these other free variables in. So you then have to start worrying about how long the formula is, and how many free variables it's got, which H's are going to be good for this and good for that. But it's quite succinct if you just say, well, consider H's which are infinitely long, even if from some point onwards they just return the same object. Because then I don't have all this fuss. I don't have this worry. Because this assignment function that makes this chi, which is v0, come out true, actually has got domain omega, and it assigns something to all free variables. So I can consider it as a potential assignment function to make psi true. So then I don't have this worry. So this step here is made easier by assuming that dom H is omega. So it's a quick way of defining satisfaction. It speeds up the definition of satisfaction by having H's which are infinitely long. Okay, so that's the satisfaction relation. Just to preview a little bit of what's going to come next, we're going to formalize definability. And we're going to define a function def. And what's the idea? The idea is def of x This will be the collection of all subsets of X which are definable by a formula. Definable by a one free variable formula. Actually, it'll be useful to think of formulae with more free variables because we'll put parameters in for the other variables that are not free. So here's a structure X. I might be able to define this part of X by some formula. So a subclass of X by formula phi v0. For example, if X is the natural numbers, omega, I could define what the evens are. I could write out a formula that gives me which things are the evens. So we want to do this in general. So I want to think about all the subsets of X that I could define by a formula like this. Now, we allow ourselves parameters in these definitions. I can write down what the set of evens is without referring to any other objects. But if I want to say the set of evens bigger than 24, I'm going to have to make reference to the number 24. So it will be useful to have a formula that can talk about 24. And the formula phi now would say any even number bigger than this. So it's useful to have 24 as a parameter in that definition. And we'll allow that to happen. We'll think about formulae where they're actually, it's got more than one free variable in. The thing is, we'll fill up the other free variables with parameters. So we'll actually allow formulae with more free variables, which we'll think of the assignment function as which we'll think of the assignment function h as supplying parameters from X for the definition. And what are the parameters here will be, well, h1, h2, up to hk, to use in the definition. But we'll always keep v0 free to be the things that we can consider. So v0 is free for us to put natural numbers in, say, right? Or any set, actually, of course. But and for some, formula will be true if I substitute in an even bigger than 24. And for some, it'll be false. So the formal definition of that is 317. What is def X? It's going to be a collection of objects. Here's a set defined by the definition phi. Put in W for V0. So this is a subset of X defined by the formula phi v0, where U is the code of phi. And we allow here, we take a fixed H, which will assign objects to other free variables in phi. But now we look and see if we tweak H and let for v0 be all the possible W's there are in X, some will become true in X, in which case we'll put them in the set. And the others for which this doesn't hold, then we leave it out. And so def X will be the set of these things. And let's give this a name, right? This is iota for historical grounds. X union H is this set here. So this is what I'm calling iota of X and U and H. It only depends upon these objects here. Right? Def X is the set of all of these. H here, such that this is a formula, and H is an assignment function of the appropriate kind.